Hey, good morning, guys. So today we're going to take a look at a review about, or an introduction, I guess, about some of the structure of the electron cloud, how the electron cloud is divided up into energy levels, which even Bohr knew about, but then into the more exotic things like sublevels and orbitals and some of the funky things that go along with those particular pieces. So from way back when, our friend Bohr here knew about the planetary model. His idea was that there was a nucleus in the center with protons and neutrons in it, and that electrons could jump from one energy level, the ground state, to a higher energy level, to an excited state, if they absorbed energy. And then when they fell back down, that they could release some of that energy, that we could see that energy then as light. That's the basis of the whole emission spectrum that we looked at in class, and that's how he sort of came up with that idea of energy levels. So he was the first guy to really start to think about what electrons are doing and kind of how are they moving around. And again, it worked in terms of the emission spectrum for hydrogen, that we can picture those colors of light that are created by hydrogen from electrons jumping up to a higher energy level, absorbing some energy, and then releasing energy as they jump back down. And this was great, except that it really didn't work for anything other than hydrogen. It kind of worked for helium, but bummer. So with this, they had to kind of go a little bit further and realize that there was more things going on than just this basic bit of sublevels or energy levels. So the next idea that came along that helped to explain atoms that were at all more complex than hydrogen, like helium, etc., was that maybe it's not just a plain energy level. Maybe an energy level isn't one thing, but maybe it's actually made up of multiple things. And this is where the idea of sublevels, or in this diagram as it shows it, subshells, came from. I will use the term sublevels, although the term subshells is also used. And so as they started to look at the evidence for it, they started to realize that each energy level could be broken down a little bit further. And you can kind of see that the pattern here is a fairly straightforward pattern. When he started to look at this and looked at these more complex light patterns, he realized that there was more jumps available than he originally thought, because more different colors of light were being produced. So these sublevels have evidence from the emission spectrum, especially when they started talking about hydrogen and lithium. They could see that right away, that yeah, this starts to make a lot more sense, that it's not just energy levels, but there's like little mini steps within there. And the pattern's pretty easy. The first energy level has one sublevel, second energy level has two sublevels, and the third energy level has three sublevels. And again, that was pretty well supported by the emission spectrum of larger atoms, some of them anyway. As we moved on, we started to come up with, had to have ways to talk about these, right? The number of sublevels that's in each energy level, the pattern's pretty obvious, it's kind of nice actually, is that the number of sublevels is equal to the number of the energy level. So for energy level number 1, it only consists of that one level. So we could say it's one sublevel, but it's the level. Energy level 2 is broken down into 2 parts, and those are called sublevels. Energy level 3 has 3 sublevels. So far so good, right? This is a nice easy pattern. This does seem to continue all the way up to 4, 5, and 6, even though we don't really draw those that much. Thank God it's not something more complex, because as we get into the next part, it gets a little bit weird. So each sublevel has its own name. It would have been really nice if they just used A, B, D, and C, but they didn't. The first sublevel is always called an S. It's just kind of one of those weird things that they are. Like I said, it's kind of like if we use it like 2A, 2B, 2C, well, it's called an S. That's just what it is. The first energy level has one sublevel, so it's called the 1s. First energy level, S sublevel. In the second energy level, there's 2 sublevels. There's the S and the P. It's kind of like saying A and B. So these are called 2s because they're on the second energy level, and 2p. And that kind of makes sense. Helps to distinguish it between the 1s and the 2s, so that's why you have to have the number out in front. Third one has 3 sublevels. They're S, P, and then D is the third one, so 3S, 3P, and 3D. And then the fourth one has 4 sublevels, is where the F comes into play. 4S, 4P. Wow, I forgot to fix this. 4S, 4P, 4D, and 4F. No, 4, 4, and 4. Sorry, 4S, 4P, 4D, 4F. And yes, there would actually be higher energy levels as we get up to number 5, 6, and 7, but we don't really talk about those too much, so don't stress about them. So S, P, D, and F in that order. 1S, 2S, 2P, 3S, 3P, 3D, 4S, 4P, 4D, and 4F. Here's the messy part. It turns out that these three-dimensional shapes, these sublevels, are actually related to probabilities. When they started to map out where the electrons were, sort of a way of taking a type of a snapshot, you get images that look like this. And some of the early images, like for the 1s, are actually very, very similar to this, where you just see something that looks kind of like a fuzzy sphere, which is kind of nice. Most of the electrons, about 90% of the time, they're located in this central part of this, although occasionally they can find themselves in crazy locations, just sort of depending on chance. So that 90% chance space right there, for this, we call it a fuzzy sphere. It's not a hard shell, it's not a true circle, and we call it fuzzy because, again, they can sometimes are inside, sometimes they're outside, so the edges are kind of blurry of that, so we just call it a fuzzy sphere. When we get into the bigger energy levels, however, things start to get a little bit ugly. This is what the second energy level looks like when we start to break it apart. And here you can start to see that idea of an energy level and a sublevel. So when we start to take a look at it, this picture on the left here is still that kind of sphere shape. But these pictures on the right, definitely not sphere shape. There's just something funky that's going on over here. We knew that there was two sublevels, S and P, but yet when we do the map, we get something more than that. We get a couple of different pictures to it, so that's kind of weird. The S sublevel was as we predicted. It's pretty much a sphere shape to it, and you can kind of see it over there on the left. It's bigger than the first one. Here's like the 1s inside of there, and then there's the 2s outside of there. So they basically have the same shape. The 2s is just a lot bigger. However, the P sublevel was further subdivided, I guess you want to think about it. There's a couple of different shapes to it. It's kind of a fuzzy dumbbell shape. It looks a little weird. It's kind of a bimodal distribution. There's a kind of a lump down here and a lump up here. And when you kind of draw a picture around it, it looks like this sort of a fuzzy dumbbell kind of a shape. Again, my computer drawing skills aren't that great, so imagine that it's that particular shape. But they realized that there was more than just one of them. There was actually two of them, an up-down one and a left-right one, and then there's even a third one, which isn't shown in this picture, and the third one was oriented this way, in and out, so that's kind of why it's not drawn. It wouldn't look very good if you tried to draw it coming straight out of the mirror at you, or out of the computer at you. So that P sublevel, yeah, there's a P shape, but the P shape is further divided into three different versions of it, an up-down, a left-right, and a front-back. So they had to kind of come up with a way of discussing these sub-levels in a way that made sense. So these things are called orbitals. And the orbitals are simply a reflection of these probability maps, that they have a particular shape, but then they also have a particular orientation in space. The sublevel is the shape. So the S sublevel has this particular shape, and the P sublevel always has that particular shape. There's that fuzzy sphere, fuzzy dumbbell kind of shape, and here you can kind of see what that inny-outy one kind of should look like. We call those fuzzy dumbbells, which is fine. The orbital is simply which one is it? Is it this particular X, or P? Is it this particular P, or is it the third possible P? So we call them PX, PY, and PZ. I'm not going to test you on that at all, but know that there's three different orientations. S has one, and then the P is further broken apart into three. Yikes, right? It's still considered a three-dimensional region, and that orbital space is still considered to be that 90% of the time. So S has one, P has three, and now we'll take a look at what the D's look like, because yeah, they're scary. Turns out the D sublevels are even more complex, as we're trying to fit more and more electrons into that scary space that they're trying to get into. The electrons, in a sense, have to get more and more creative about how they're sort of spending their time. So these sublevels for the D is further divided into a bunch of different orbitals. And in fact, it's 5. Most of the shape of these, the D sublevels, tends to be fuzzy clovers, except for this cool one, which is a dumbbell with a donut around its middle. I like that one, that's my favorite. But most of these are kind of fuzzy clover leaf shapes. They've got the 4 different lobes to them. And again, with these more complex shapes and more electrons to it, that 3D sublevel, it's pretty big. They needed to get more complex three-dimensional shapes to make the electrons be able to split up that space. In this case, we've got 5 different orbitals. It was 1 for S, 3 for P, and 5 for D. It's a pattern of odd numbers. And then the F is even the next step up from that, where it's got 7 different orbital orientations, even more complex, crazy-looking shapes in terms of what they are, but there happens to be a series of 7 of them. So again, if you can remember the odd numbers, the number of orbitals is 1 for S, 3 for P, 5 for D, and 7 for F. 1, 3, 5, and 7. There we go. Last piece, here's another kind of way that you may see these represented. Here's what the S sublevel looks like. Here's what the P sublevel looks like in all of the 3 different orbitals for the P. Here's what the D sublevel looks like down here at the bottom. And again, it's got 1, 2, 3, 4, 5 different possible orientations, including the one fuzzy different shape that's in the middle there, but we call those fuzzy clovers. Each of these particular spaces here, and again, these are called orbitals, each individual one can hold 2 electrons. They kind of end up sort of at opposite ends. So like 1 electron's over here, and then 1 electron's over here, and then sometimes they switch spots in terms of where they are. Like for example, in these ones down here, you'd have 1 electron kind of taking up that space, and the other electron would be kind of taking up that space. Or down here, 1 electron in the vertical part, and then 1 electron in the donut. It's kind of how they sort of flip around. But they can hold 2 electrons each. So what this means is it gives us a total number of electrons. An s orbital with its one shape can hold 2 electrons maximum. A p orbital is, well, each one of them, each p orbital can hold 2. There's 3 of them altogether, so you get a total of 6 electrons can be in a p sublevel, because you could have 2 in this one, 2 in this one, and 2 in this one. These are what we're going to use later on in our orbital diagrams, which kind of make it kind of nice. Our third one is the d orbitals down here. Again, each one of these can hold 2, so you can have 2, 4, 6, 8, and 10 maximum in there, which is a total of 10 electrons in the d sublevel. Each orbital, d orbital, holds 2. The total, all the d orbitals together, can hold 10. And the f, again, had 7 different orientations to it. F had 7 orbitals. Each one of those holds 2 for a total maximum of 14 electrons. Quite a lot actually could fit in those f sublevels. So they're absolutely huge. So there's got to be an easier way to kind of draw all these. Keep in mind that as we're going through this, as we get to these bigger and bigger energy levels, because each bigger energy level has more sublevels to it, each sublevel has more orbitals to it, and again, this is a way for us to get 55 electrons, 79 electrons, 118 electrons, all whizzing around at the speed of light to not crash into one another and to conveniently and easily use a very small space, which is that electron cloud of that atom, in a way that works for these things. So again, as we get larger to the 2nd, 3rd, and 4th energy level, we have to divide it into more sublevels to kind of even that part out, and then more orbitals within there so those electrons don't physically crash. I kind of joke about it being a lot like Christmas time when you've got more and more people visiting your house, and your house was fine with just 2 of you in there, and as you're trying to cram more and more people in there, you either need to get a bigger house with more rooms, or you really got to get creative about how you start to subdivide that space so that you all don't mash into one another or, you know, get into fights over the bathroom, whatever it is. As we're getting up into these other ones, I was kind of talking about this earlier, that as we get to each energy level, the total number of electrons gets bigger and bigger and bigger. So as you can kind of see the pattern here as it works out, each energy level has a certain number of sublevels. Those sublevels have a certain number of electrons, orbitals to them, and each orbital can hold 2 electrons. So your maximums for each one of these, the first energy level has a total of 2 that it can hold, S sublevel with 2 electrons in it. The second energy level has S and P sublevels, so it can hold 2 plus 6 makes a total of 8 electrons that can fit total in everything that the second energy level has to offer. Third energy level is the biggest one yet, that it has even more to offer. It's got an S sublevel, it's got a P sublevel, and it's got a D sublevel to it with 2, 6, and 10 electrons in it, and that gives you a total of 18 electrons that can fit in that third energy level. It's actually quite large. F is even bigger. I'll let you figure out what that would be. So when we're trying to draw these, man, trying to draw these shapes, that's kind of a pain in the butt. And we needed a simpler way to represent these on paper. So we're going to use this thing called an orbital diagram. It's simply a shortcut. Rather than trying to draw all those crazy shapes and rather than trying to draw them all out, we're going to use something very simple. We're going to use circles. Sometimes you'll see squares, other things like that, but we're going to use circles to represent each orbital. So P had 3 of them. We're going to draw 3 little circles to it rather than trying to draw 3 fuzzy dumbbells or 3 clovers or 3 dumbbells with donuts on them. It just makes it a lot easier. The first energy level has 1 sublevel, so you draw 1 square or 1 circle for it. The second energy level has 4 squares to it. It has the S sublevel with 1 circle, and the P had 1, 2, 3 to it. So you're going to draw a total of 4, 1 S and 3 Ps. You have to draw the full set. So when you're drawing these, and we'll come back to these here in an example, that if I'm going to start to draw P orbitals, I have to draw all 3. I'm not allowed to just draw one of them. If I'm going to draw a D sublevel, I have to draw all 5 orbitals, and if I want to draw an F, I have to draw all 7 of them. You're not allowed to just draw the first one or the first and second one. You have to draw the full set every time you start. We're going to use arrows then to represent where these electrons are. And remember that each orbital can hold 2 electrons. We're going to represent those with arrows. We're going to call them up and down arrows. It is all right when you're drawing these to have empty boxes or empty circles as you're drawing these out. Here's an example of what one looks like. So this would be the orbital diagram for oxygen. Oxygen has a total of 8 electrons that we have to figure out where these things go. So they start off in the first energy level, and they could fit into the S sublevel. So we're going to draw one circle, or in this case a square, and we're going to fill that up because we've got enough room to put those 2 electrons in there. The next thing that fills up, because we've got a bunch more electrons we've got to deal with, is going to be the second energy level. So I'm going to start by drawing the 2s circle right here, or the 2s square, I guess, sorry. And I can put 2 more electrons in there. Remember, the S sublevel has 1 orbital to it, so we draw 1 square. It's full, it's got those 2 electrons in it. Now I've drawn 4 electrons. I have more that I have to draw, 4 more as a matter of fact. So here they are right here. I'm going to draw them out. I'm going to have to draw my P sublevel now and put electrons into there. Come back here. I don't want my Adobe Reader, thank you. Come back here, there we go. Sorry about that, weirdness. So with this one, I had 4 more electrons I had to take care of. So I put 1 in the first p orbital, 1 in the second p orbital, 1 in the third p orbital, and then I got them back and started to get roommates there. So there's my last 4 electrons hanging out in that 2p sub-energy level, if you want to call it that. So these are a little bit crazy. We're going to do plenty of these in class in terms of drawing those orbitals, orbital diagrams. I've got a second little video about just practicing writing those orbital diagrams, so I just sort of introduced it here. That'll give you a lot of examples about how to draw those out. So the electron cloud, kind of in summary, there's a heck of a lot more to it than we originally thought. There's levels, there's sublevels, there's layers and sublayers and fuzzy shapes and all kinds of craziness going on there. It's not just the simple energy levels. So that's what we thought, and that's great. Bohr had the right idea to start, that there was energy levels, energy level 1, 2, 3, and 4, and each energy level is larger and gets kind of further away from the nucleus. We also now know that each energy level gets more complex in terms of the way that it's subdivided. So we have sublevels in many of these energy levels, and so each level is kind of broken down. They're given names, S, P, D, and F. Again, that's kind of like saying sublevel A, sublevel B, but they have funky letters to them. I'll let you Google what those letters stand for if you really want to. We don't really care. I'm never going to test you on it, but they're just called S, P, D, and F. And each of those sublevels is associated with a unique shape. And again, it's just a way of subdividing that 3-dimensional space. Those 3-dimensional spaces, then, we start to call those orbitals, because orbitals are the spaces where we're breaking those sublevels down even further, and this is kind of where those electrons are hanging out. Each one of these spaces refers to a specific orientation in space of those unique shapes. So if we're talking about the shape of a P sublevel, which is this fuzzy dumbbell, the orbital refers to which fuzzy dumbbell is it, which orientation in space is it. Remember that each orbital, or each set of orbitals is associated with an odd number. So for an S sublevel, there's 1 orbital. For a P sublevel, there are 3 orbitals, 3 orientations. For a D sublevel, there's 5 possible ways that that thing can orient in space. And for an F sublevel, there's 7 possible orientations in space for it. And then the last thing is to remember that when we're doing the electron cloud, each one of those orientations, each one of those sub levels can hold 2 electrons. That's called spin, and we use an up arrow and a down arrow to kind of deal with those things. So that last little piece is a way to kind of draw them all out rather than trying to draw these crazy shapes. We're going to totally simplify and draw each one like its own individual circle, even knowing that those circles represent crazy, weird 3-dimensional shapes that are all overlapping with all kinds of craziness. Simple circles, simple arrows, just an easier way to represent them, and those are called orbital diagrams. So there you go. A lot more detail about the structure of the electron cloud and all the little pieces that are inside there. Like I said, it's way crazier. I see why they call it a cloud, because man, if you can imagine all those shapes overlapped on top of one another, you looked at it from a distance, it would just look like a cloud, just of electrons just going like crazy in there. There you go, electron cloud. Hope you enjoyed this, and like I said, for extra credit, you can look up the shapes of the F orbitals and figure out what those are. They're crazy. Like them. All right, have a good day, and I'll see you in class tomorrow.